Hello there, stargazer. Welcome to Snoozing Ideas channel, where tonight we meet at that perfect intersection of wonder and rest. I can see you're here, perhaps with heavy eyelids or a busy mind that needs gentle quieting. That's exactly why I'm here, to accompany you into peaceful slumber while traveling through the cosmos together. As you settle in, allow your breathing to deepen, your shoulders to soften, and your thoughts to float as weightlessly as an astronaut drifting through the International Space Station. Tonight, we'll explore the most peaceful aspects of our universe. The silent dance of distant galaxies, the patient light that travels billions of years just to reach your window, and the comforting vastness that makes our worries seem appropriately small. Space isn't just an endless void. It's a tapestry of calm, waiting to wrap around your consciousness. Let's begin. The Milky Way has been our cosmic home for billions of years. Our galaxy stretches across 100,000 light-years of space, containing approximately 400 billion stars arranged in graceful spiral arms that curve through the darkness. Astronomers have mapped these structures using radio telescopes that peer through the dust clouds obscuring our view, revealing a barred spiral pattern with elegant symmetry. The oldest stars in our galaxy have been shining for more than 13 billion years, witnessing the slow evolution of cosmic structure. What stories could they tell if we could understand their light? Like an ancient tree, with rings marking centuries, our galaxy carries the subtle traces of its history in the motion and composition of its stars. Nebulae float like celestial clouds in the vastness between stars. These massive formations of gas and dust drift through space for millions of years, their delicate tendrils slowly condensing into new stellar formations under gravity's patient hand. The famous Orion Nebula spans 24 light-years, containing enough material to form thousands of new stars. Within these cosmic nurseries, matter gradually clumps together, growing denser until nuclear fusion ignites a newborn star. Some nebulae glow from within, illuminated by the very stars they helped create. Their shapes evolve with imperceptible slowness, transforming over timescales that make mountains seem ephemeral. Each nebula, a tranquil garden where stars are quietly cultivated. Galaxies turn with a patience beyond human comprehension. Many spiral galaxies complete just one rotation every 200 million years, carrying their solar systems in vast, unhurried circuits through the cosmos. Our own solar system moves at about 828,000 kilometers per hour around the galactic center, yet takes 225 million years to complete a single orbit. The last time our sun was in its current galactic position, dinosaurs were just beginning to walk the Earth. Even at such tremendous speeds, the movements appear frozen to human observers due to the immense distances involved. The stars we see tonight occupy nearly the same positions as those gazed upon by the earliest humans. Sometimes, galaxies meet in the darkness, merging over billions of years. When two galaxies begin their slow collision, their stars sail past one another without a single impact, separated by distances so vast that direct collisions are virtually impossible. The antennae galaxies have been merging for over 400 million years, their gravitational dance distorting their elegant spiral shapes into long tidal tails of stars. Gas clouds do interact, however, triggering bursts of new star formation that illuminate the joining bodies. These cosmic encounters reshape galaxies without violence or destruction, more like a gentle blending of rivers than a collision of objects. Gravity weaves two separate histories into one new shared future, patient and inevitable. In the vacuum of space, perfect silence reigns eternal. Without air molecules to carry vibrations, sound cannot travel, creating a realm of absolute quiet that stretches across the cosmos. Even the most catastrophic events, supernova explosions that outshine entire galaxies, occur in this profound stillness. Scientists can translate electromagnetic waves from space into audible sounds for human perception. But these are interpretations rather than actual cosmic sounds. Could there be forms of perception beyond our understanding that experience the universe differently? This silence forms the backdrop for all cosmic drama, a canvas of quietude upon which the light of stars paints its stories. Stars maintain a respectful distance from one another in the cosmic neighborhood. The average separation between stars in our galaxy is approximately 4.2 light-years, creating vast, empty regions that dwarf the stars themselves. Our nearest stellar neighbor, Proxima Centauri, sits at this typical distance, with light taking over 4 years to bridge the gap between us. These enormous voids ensure stellar systems rarely disturb one another, allowing planets to orbit peacefully for billions of years. The emptiness between stars consists of extremely thin gas and dust, just a few atoms per cubic centimeter. In this arrangement, stars resemble lonely islands in an ocean of darkness, each one a distant lighthouse visible across the void. Exoplanets circle their stars in cosmic rhythms as ancient as time. Most discovered exoplanets orbit their parent stars in periods ranging from mere days to several Earth years, following paths prescribed by gravity's unwavering hand. The closest orbit belongs to Sweeps 10, which circles its star every 10 hours. Astronomers detect these distant worlds primarily by measuring the slight dimming of starlight as planets transit across their stars. The regularity of these orbits forms a kind of cosmic clockwork, each planet returning to the same position with perfect precision. Like pendulums marking time on an astronomical scale, these distant worlds trace their elliptical paths through space with mathematical certainty. Between Mars and Jupiter floats a peaceful realm of ancient stone. Some asteroid belts contain millions of rocky objects that have orbited in stable patterns for billions of years, remnants of a planet that never formed. The largest, Ceres, measures just under 1,000 kilometers in diameter, while most are smaller than mountains. Despite science fiction depictions, these rocks typically maintain distances of hundreds of thousands of kilometers from each other. The total mass of the main asteroid belt equals just 4% of our moon, spread across a volume of space that could fit 150 Earths. This sparse distribution allows spacecraft to navigate safely through without collision. Each asteroid carries a record of the early solar system, unchanged since its formation. Binary stars dance together in the darkness of space. Many pairs of stars orbit their common center of mass in stable patterns that remain unchanged for eons, bound by gravitational attraction that neither weakens nor falters. Some complete their orbits in days, others in centuries, but all maintain their celestial choreography with unwavering precision. Astronomers have documented over 130,000 binary systems in our galaxy alone. The components exchange material in some cases, their stellar atmospheres flowing between them like cosmic rivers. Despite these interactions, many binaries maintain their separate identities for billions of years. Like partners in an eternal waltz, they move in perfect synchrony, neither accelerating nor slowing as they trace their paths through the void. A whisper from the beginning of time bathes every point in the universe. The cosmic microwave background radiation fills all of space uniformly at a temperature of 2.7 Kelvin, just barely above absolute zero. This faint afterglow comes from approximately 380,000 years after the Big Bang, when the universe first cooled enough for light to travel freely. Scientists mapped this radiation with increasing precision, revealing tiny temperature variations that seeded the formation of galaxies. These almost imperceptible fluctuations, just one part in 100,000, grew over billions of years into the cosmic structures we see today. What mysteries might be hidden in those ancient patterns? Like the soft glow of embers from a long extinguished fire, this radiation carries the memory of cosmic dawn. Some regions of the cosmos approach perfect emptiness. In certain voids, between galactic superclusters, the density of matter is less than 1 atom per cubic meter, creating spaces of near absolute nothingness that stretch for millions of light years. The Boötes void spans approximately 330 million light years, yet contains few detectable galaxies. These cosmic deserts formed as matter gradually migrated toward denser regions under gravity's influence, leaving behind increasingly empty spaces. The universe continues this process of cosmic organization, with voids growing larger as matter concentrates into filaments and clusters. These vast empty regions serve as the negative space in the universe's structure, defining the boundaries between the cosmic web's luminous threads. Pulsars keep time with supernatural precision across the stars. Some of these spinning neutron stars emit radio waves with timing that rivals atomic clocks, rotating hundreds of times per second without variation. The first discovered pulsar, PSR B1919 plus 21, completes one rotation every 1.3373 seconds and has maintained this exact period since its discovery in 1967. These collapsed stellar cores contain the mass of our Sun compressed into a sphere just 20 kilometers across, spinning with such regularity that astronomers can predict their pulses thousands of years into the future. Their reliability has even allowed them to be used as navigation beacons for spacecraft. Like cosmic lighthouses, they sweep their beams across the universe with a constancy that defies imagination. Moons throughout our solar system stand frozen in eternal gaze. Many satellites are tidally locked to their planets, showing the same face for millions of years, while their far sides remain forever hidden from their parent worlds. Our own moon completed this gravitational synchronization early in its formation, with its rotation matching exactly the time it takes to orbit Earth. This phenomenon results from the slight elongation of the satellite, with the longer axis preferentially aligned toward the planet's gravitational pull. The process gradually slows rotation until perfect synchronization occurs. Across the solar system, most major moons exhibit this same patient alignment, their features forever fixed in relation to the planets they circle. A gentle breeze from the Sun stretches to the edge of our solar system. The solar wind travels at speeds of 400 to 800 kilometers per second, carrying charged particles throughout interplanetary space in a continuous stream of plasma. This invisible flow originates in the Sun's outer atmosphere, where temperatures exceed 1 million degrees Celsius, causing particles to escape the Sun's gravity. Earth's magnetic field shields us from this radiation, diverting the particles toward the poles, where they create auroras. The interaction creates a protective bubble called the magnetosphere that has sheltered Earth's atmosphere for billions of years. Like a cosmic weather system that never changes, this wind blows outward in all directions, touching every planet and moon in its path. Some comets follow paths of extraordinary patience through the void. These icy wanderers traverse elliptical orbits that take them thousands of years to complete a single revolution around the Sun. Comet Hale-Bopp, which last graced our skies in 1997, won't return for approximately 2,500 years. These ancient travelers spend most of their lives in the distant outer solar system, moving slowly through the darkness, far from the sun. As they approach the inner solar system, solar radiation vaporizes their ices, creating the characteristic tails that can stretch for millions of kilometers. Many comets have orbited unchanged since the solar system's formation. What distant stars might they have passed on their long journeys between visits to our neighborhood? At the edge of our solar neighborhood lies a subtle boundary few will ever see. The heliopause marks the limit where the solar wind meets interstellar space, approximately 120 astronomical units from the Sun. A distance light requires 16 hours to cross. Only the Voyager spacecraft have crossed this threshold, entering the space between stars where particles from other suns outnumber our own. Scientists detected this transition when Voyager 1 recorded a sudden change in the surrounding magnetic field in 2012. Beyond this boundary, the protective influence of our star fades away, replaced by the collective influence of distant suns. Like shores meeting an ocean, this invisible line separates the familiar waters of our solar system from the true cosmic deep. Star clusters hold together in cosmic family units across eons. Many clusters contain hundreds of stars that formed from the same molecular cloud over similar timescales, sharing chemical composition like siblings with common ancestry. The Pleiades, visible to the naked eye, contains over 800 stars formed together about 100 million years ago. These stellar communities travel through the galaxy as a unit, maintaining their gravitational bonds despite external forces that would pull them apart. Young clusters shine brilliantly with massive blue stars, while ancient globular clusters glow with the softer light of stars that have burned for billions of years. Like villages that have wandered the cosmic countryside since ancient times, these stellar groups preserve their connections across enormous spans of time. Earth maintains a perfect, unwavering pace in its journey around the Sun. The orbital velocity of our planet remains constant at 29.78 kilometers per second, a speed that has varied little over billions of years. This precise movement keeps us in a stable orbit approximately 150 million kilometers from the Sun, within the narrow habitable zone where water remains liquid. Our planet covers 2.6 million kilometers each day, yet we feel no sense of motion. The stability of this orbit has allowed life to evolve without catastrophic climate shifts that would occur with significant orbital changes. Like a cosmic metronome marking the years, Earth's orbital constancy provides the reliable foundation upon which the story of life has been written. White dwarf stars cool with infinite patience in the darkness. These stellar remnants, having exhausted their nuclear fuel, gradually fade from white to yellow to red over billions of years as their residual heat slowly radiates away. A typical white dwarf, compressed to the size of Earth, but containing the mass of the Sun, begins its cooling phase at temperatures exceeding 100,000 Kelvin. The oldest known white dwarfs have cooled to about 3,000 Kelvin over 10 billion years, yet remain warm enough to glow visibly. Given enough time, trillions of years, these stars will eventually cool to become black dwarfs, though the universe is still too young for any to have reached this state. Like embers outlasting the fire that created them, these ancient stellar cores quietly witness the passage of cosmic ages. In globular clusters, stars maintain harmony despite their numbers. These ancient stellar congregations contain hundreds of thousands of stars orbiting a common center in stable patterns that have persisted for over 10 billion years. Some of these clusters, like Omega Centauri, may contain more than 1 million stars within a sphere just 150 light-years across. Despite their density, stars rarely collide, maintaining their individual orbits through delicate gravitational balance. Many globular clusters formed in the early universe and have survived essentially unchanged since then, making them among the oldest structures in the galaxy. Their stars move in three-dimensional orbits that create a spherical formation, like silent chimes suspended in perfect equilibrium around a central point. Jupiter's magnetic presence extends far beyond its visible form. The magnetic field of this gas giant stretches millions of kilometers into space, creating a magnetosphere larger than the Sun itself. Generated by currents in Jupiter's liquid metallic hydrogen layer, this invisible force deflects the solar wind and traps charged particles in radiation belts thousands of times more intense than Earth's. The field stretches so far that it affects the orbits of nearby moons and occasionally interacts with Saturn's magnetosphere. If visible to human eyes, Jupiter's magnetic bubble would appear larger than our moon in Earth's sky, despite being over 600 million kilometers away. Like an emperor's unseen influence extending beyond his kingdom, Jupiter's magnetic reach silently shapes a vast region of interplanetary space. The rings of planets consist of countless silent particles in eternal orbit. These formations, most dramatically displayed around Saturn, contain billions of ice and rock fragments ranging from dust grains to house-sized boulders, each following its own orbital path. Saturn's main rings span 280,000 kilometers, yet average less than 10 meters thick, proportionally thinner than a sheet of paper. Despite their apparent solidity when viewed from Earth, the rings are mostly empty space, with particles typically separated by distances many times their size. These fragments have maintained their collective pattern for millions of years, creating structures that appear unchanging despite their component parts being in constant motion. Like cosmic rivers frozen in circular paths, they flow perpetually around their planetary anchors. Venus rotates with unusual deliberation against the cosmic norm. The rotation period of our neighboring planet spans 243 Earth days, longer than its orbital period of 225 days around the Sun, making it the slowest rotating planet in our solar system. This means that on Venus, a single day outlasts its entire year. The planet also rotates retrograde, opposite to most planetary rotation, possibly due to an ancient collision that reversed its spin. This peculiarity creates an extraordinary lengthening of day and night, with each lasting approximately 117 Earth days. The Sun rises in the west and sets in the east on Venus, crossing the sky with imperceptible slowness. Like a cosmic contrarian, Venus maintains its unhurried pace against the regular rhythms of the solar system. Meteorites carry messages from the birth of our solar system. Some that reach Earth originated from asteroids that formed 4.6 billion years ago, containing materials unchanged since the solar system's earliest days. These cosmic messengers occasionally fall through our atmosphere, bringing samples of space directly to Earth's surface. The oldest components in these rocks, called calcium-aluminum inclusions, formed when the solar nebula was still condensing into planets. Scientists have recovered approximately 70,000 meteorites worldwide, each containing clues to our origins. The Murchison meteorite, which fell in Australia in 1969, even contains amino acids, building blocks of life, that predate Earth itself. Like letters from a distant past, these ancient stones whisper stories of a time before our world existed. Jupiter's Great Red Spot has watched over the solar system for centuries. This massive storm has been observed for over 400 years, maintaining its structure across the generations of astronomers who have studied it. Spanning 16,000 kilometers, wide enough to engulf Earth, this anticyclonic storm rotates counterclockwise with wind speeds reaching 432 kilometers per hour at its edges. Though it has gradually shrunk since detailed observations began, the storm shows no signs of disappearing completely. Within its swirling clouds, lightning flashes and atmospheric chemicals create its distinctive reddish hue. Temperatures at its center dip to -160 degrees Celsius. Like a meditative whirlpool in Jupiter's atmosphere, the Great Red Spot continues its endless turning, indifferent to the passage of time. Some satellites hang motionless in the sky, frozen in cosmic balance. Many communication satellites maintain geosynchronous orbits 35,186 kilometers above Earth's equator, appearing stationary relative to the ground below. At this precise altitude, their orbital period exactly matches Earth's rotation, 24 hours, allowing them to hover over the same location continuously. This mathematical harmony between gravity and centrifugal force creates a perfect equilibrium that requires minimal fuel to maintain. Thousands of these satellites occupy this special orbital region, forming a ring around our planet that follows natural physical laws. Each one stays perfectly aligned with its ground stations for decades. Like patient sentinels, they maintain their positions in the sky, suspended in gravitational balance. Escape velocity follows one unchanging rule across the cosmos. The speed needed to break free from Earth's gravitational pull is 11.2 kilometers per second, regardless of the object's mass or composition. This physical constant means that a feather and a boulder require the same initial velocity to leave Earth's influence forever, though air resistance affects their actual trajectories. This principle applies throughout the universe. Each celestial body has its own escape velocity based solely on its mass and radius. For the Moon, it's just 2.4 kilometers per second, while for a black hole, escape velocity exceeds the speed of light. The mathematics governing this phenomenon has remained unchanged since the universe began. Like an invisible threshold that separates the bound from the free, escape velocity defines the energetic boundary of every world. Brown dwarfs occupy a twilight realm between planets and stars. These curious objects emit heat from their formation for billions of years, without undergoing the nuclear fusion that powers true stars. Too massive to be classified as planets, yet too small to ignite hydrogen fusion, they glow faintly in infrared light from their residual formation heat. The youngest brown dwarfs shine with temperatures around 2,200 Kelvin, gradually cooling over billions of years to space-like temperatures. Scientists have discovered over 2,800 of these failed stars in our galaxy. Some are massive enough to briefly fuse deuterium in their cores before this limited fuel depletes. Like cosmic embers that never quite caught flame, these objects slowly exhale their heat into the surrounding void, cooling with infinite patience. Our entire solar system drifts along a vast celestial circuit. The galactic year, the time for our solar system to orbit the Milky Way's center, spans approximately 225 million Earth years, creating a cosmic calendar beyond human comprehension. During this journey, we travel approximately 225 million kilometers every year through the Orion arm of our spiral galaxy. The last time our solar system occupied its current galactic position, Earth's continents were unified in the supercontinent Pangaea, and early dinosaurs were just beginning to evolve. Despite this immense journey, the stars around us appear nearly fixed due to their similarly vast movements. Could there be patterns in our galactic orbit that affect Earth? Like a celestial carousel, our entire planetary system follows this grand circuit through space. Craters on airless worlds stand as monuments to time's passage. Many impact structures on bodies without atmospheres preserve their original form for billions of years unchanged, creating a permanent record of ancient cosmic collisions. On Earth, erosion erases impact evidence within thousands of years. But on the Moon, Mercury, and asteroids, craters from the solar system's earliest days remain visible. The lunar crater Tycho formed approximately 108 million years ago, yet looks freshly made to observing telescopes. Even footprints left by Apollo astronauts will likely remain visible on the lunar surface for millions of years. In the absence of wind, water, and weather, these scars heal only through the incredibly slow process of micrometeorite erosion. Like cosmic museums, these worlds preserve their histories with perfect fidelity. Earth's seasons follow a rhythm set by celestial geometry. The axial tilt of our planet at 23.5 degrees creates the seasonal cycle that has remained stable for millions of years, allowing life to adapt to its predictable variations. This slight leaning of Earth's axis relative to its orbital plane means that northern and southern hemispheres receive varying amounts of sunlight throughout the year, creating the familiar pattern of summer and winter. The stability of this tilt, maintained by the gravitational influence of our moon, has prevented extreme climate fluctuations that would occur if the angle changed significantly. Without this steady orientation, life might have developed very differently on our world. Like a spinning top that maintains its angle, Earth preserves its tilt against the forces that would disturb it. Neutron stars contain magnetic power beyond human comprehension. Some of these collapsed stellar cores generate fields trillions of times stronger than Earth's magnetic field, powerful enough to distort the atomic structure of matter and create exotic states of plasma in their vicinity. The strongest measured field belongs to magnetar SGR 1806-20, with a strength of 10^15 Gauss. At close range, such fields would erase credit cards from 100,000 kilometers away and be fatal to humans at much greater distances. These fields form when the dying star's magnetic field is compressed along with its matter into a sphere just 20 kilometers across. Most neutron stars complete a full rotation in milliseconds, causing their magnetic fields to sweep through space like cosmic lighthouses. What strange physics might occur in these extreme conditions? Some moons follow an ancient orbital dance with mathematical precision. The orbital resonance between Jupiter's moons, Io, Europa, and Ganymede, has persisted for billions of years, creating a pattern where Io orbits Jupiter exactly 4 times for every 2 orbits of Europa and 1 orbit of Ganymede. This 4.21 resonance isn't coincidence, but the result of gravitational interactions that reinforce this pattern over time. The arrangement causes tidal heating that keeps Io volcanically active and likely maintains a subsurface ocean on Europa. Similar resonances appear throughout the solar system, creating stable configurations that can last for the lifetime of the planetary system. Like cosmic dancers following an eternal choreography, these moons maintain their precise timing through the ages. Human creations drift silently through the interplanetary void. Many spacecraft have been traveling through space for decades, still transmitting data as they journey farther from Earth than any human-made objects before them. Voyager 1, launched in 1977, has crossed into interstellar space and continues operating after 48 years, now more than 23 billion kilometers from Earth. Its signal, traveling at light speed, takes over 21 hours to reach us. The spacecraft carries the golden record, a time capsule of Earth sounds, music, and images, intended for any intelligence that might someday recover it. Pioneer 10 and 11 carry similar messages in the form of plaques describing humanity. These technological emissaries will likely outlast human civilization itself, continuing their journeys long after their power sources fail. Cosmic rays shower Earth with particles from distant stars. The cosmic ray background provides a constant, gentle flux of high-energy particles throughout the galaxy, most originating from supernovae explosions and active galactic nuclei billions of light-years away. These particles, primarily protons, travel at nearly the speed of light through the vacuum of space. Earth's atmosphere shields life from their direct effects, converting the incoming particles into cascades of secondary radiation. At sea level, approximately 10,000 cosmic ray particles pass through a human body each minute. The most energetic cosmic rays detected carry more energy than a professional tennis serve, concentrated into a single subatomic particle. These ancient messengers connect distant cosmic events to our world through their silent passage. New stars continue to form in cosmic nurseries across the galaxy. Some stellar nurseries continue forming new stars for tens of millions of years from the same molecular cloud, gradually converting gas and dust into brilliant new suns. The Orion Nebula has been producing stars for approximately 12 million years and will continue doing so for millions more. Within these regions, gravity slowly overcomes the outward pressure of gas, creating denser cores that eventually reach the temperatures needed for nuclear fusion. The process unfolds with remarkable efficiency, converting about 30% of available material into stars, while the remainder disperses back into interstellar space. Each new star emerges from this process with its own planetary system, continuing the cycle of cosmic creation. Like forests regenerating after a fire, these regions ensure that new stars replace those that have completed their life cycles. Earth and Moon circle a point hidden beneath our feet. The barycenter of the Earth-Moon system lies approximately under 700 kilometers below Earth's surface, creating an invisible pivot point around which both bodies actually orbit. This arrangement means Earth itself wobbles slightly as it moves through space, responding to the gravitational influence of its companion. Unlike smaller moons in the solar system, our moon contains enough mass, about 1/81 of Earth's, to significantly affect Earth's motion. This relationship stabilizes Earth's axial tilt and slows its rotation, effects that have been crucial to the development of life. The Moon continues to recede from Earth at about 3.8 centimeters per year, gradually altering this delicate balance. Like dance partners with one unseen, both worlds respond to forces centered at this hidden point. Distant worlds may harbor conditions like our own. Many exoplanets exist in the habitable zone where liquid water could theoretically exist on their surfaces, orbiting at distances from their stars where temperatures allow for Earth-like conditions. Scientists have identified over 5,000 exoplanets, with approximately 50 considered potentially habitable based on their size and orbit. The closest such world, Proxima Centauri b, orbits our nearest stellar neighbor just 4.2 light-years away. These planets range from rocky worlds similar to Earth to ocean planets covered entirely in deep water. The methods used to discover them primarily detect larger worlds, suggesting that smaller, Earth-like planets may be more common than current statistics indicate. What forms might life take in these distant environments? Like cosmic oases, these worlds represent intriguing possibilities in the vastness of space. The universe consists almost entirely of emptiness. The density of the universe is approximately 9.9 x 10⁻30 grams per cubic centimeter, mostly consisting of empty space, with matter concentrated in widely scattered galaxies. If the entire universe could be compressed with all empty space removed, it would fit within a volume smaller than a single grain of sand. Even solid objects are mostly empty at the atomic scale. The nucleus of an atom occupies just 1/4 of its total volume. This extraordinary emptiness extends across the observable universe, spanning 93 billion light-years. Between galaxies, the vacuum of space contains just a few hydrogen atoms per cubic meter, creating voids of near-perfect emptiness. Like islands of matter in an infinite ocean of nothing, galaxies themselves are mere motes in the cosmic vacuum. Warmth stirs in the darkness where no sun reaches. Some gas giant planets generate more heat than they receive from their stars through gravitational compression, their massive bodies slowly contracting under their own weight. Jupiter radiates 1.6 times more energy than it absorbs from the Sun, a surplus born from its gradual shrinking by about 2 centimeters each year. This invisible compression converts gravitational energy into thermal energy, warming the planet from within like a slowly dying ember. The process has continued since Jupiter's formation billions of years ago, a patient transformation of space into heat. On these worlds, energy flows not from above but from below, rising from cores that remember their ancient collapse from nebular clouds. The universe finds ways to warm itself even in the coldest reaches of space. Between the stars lies a gossamer veil nearly invisible to human perception. The interstellar medium stretches across light years, consisting primarily of hydrogen and helium at densities so low they would be considered perfect vacuums in any laboratory on Earth. A cubic centimeter of this ethereal matter might contain just a single atom. Yet across cosmic distances, it accumulates into vast clouds that scatter and absorb starlight. This tenuous substance is not uniform, but gathered into wisps and streams that flow between stellar islands. Radio astronomers map these invisible highways through their subtle emissions, revealing patterns that connect stellar births to deaths in an endless cycle. The apparent emptiness between stars is nothing but rather the silent breath of the galaxy itself, exhaled from dying stars and inhaled by newborn ones. Seas of stone reflect Earthlight on our nearest cosmic neighbor. Many lunar maria formed from ancient lava flows that solidified billions of years ago into smooth plains, their darkness standing in contrast to the brighter highlands surrounding them. Early astronomers mistook these basaltic plains for actual oceans, naming them maria or seas. The Mare Imbrium spans nearly 1,200 kilometers, created when lava flooded an impact basin approximately 3.9 billion years ago. These flows ceased entirely more than 1 billion years ago as the moon's interior cooled, leaving a permanent record of ancient volcanic activity. No wind or water has erased these features since their formation. Moonlight itself is simply sunlight reflecting from these ancient solidified seas, carrying to Earth the memory of fires that burned out eons before humans existed. Earth nods in a circular dance that takes millennia to complete. The precession of our planet's axis completes one full cycle every 26,000 years in a predictable pattern, gradually shifting which star marks true north. This gentle wobble, like that of a spinning top slowly losing momentum, changes which constellations appear in our seasonal skies over vast spans of time. 5,000 years ago, the North Star was Thuban in the constellation Draco, not Polaris. This celestial waltz stems from gravitational forces exerted by the Sun and Moon on Earth's equatorial bulge. The movement is imperceptible in human lifetimes, just 1.4 degrees per century. Yet ancient astronomers detected it through careful observation. Our calendars and seasons remain synchronized despite this drift, while the heavens above slowly rotate through their greater year. At the edge of our solar neighborhood waits a shell of ice older than Earth itself. Some comets originate from the Oort cloud, a spherical shell of icy objects surrounding the solar system at distances up to 1 light-year from the Sun. This vast reservoir may contain trillions of cometary nuclei, remnants from the solar system's formation preserved in deep freeze for 4.6 billion years. Occasionally, passing stars or molecular clouds disturb these ancient travelers, sending them on long journeys toward the inner solar system. The cloud itself remains theoretical, too distant to observe directly with current technology, yet inferred from the orbits of long-period comets. Each icy messenger that appears in our skies may have waited billions of years in darkness before beginning its journey inward. The cloud encompasses us like a distant memory of our system's birth, suspended in eternal night. Planets wear their colors like statements about their relationship with light. The albedo of different planetary surfaces determines how much sunlight they reflect back into space, creating the distinctive brightness and hue of each world. Venus reflects 75% of the light that reaches it, appearing as the brightest planet in our sky, despite its toxic cloud cover. Earth returns about 30%, balancing absorption and reflection in a delicate equilibrium that maintains our climate. The darkest major body in our solar system, Mercury, reflects just 7% of incident light, absorbing the rest into its heat-scorched surface. This property influences not just appearance but temperature, with high albedo worlds generally cooler than their darker counterparts at equal distances from their stars. Light itself becomes a dialogue between star and planet, spoken in photons accepted or returned to space. Stars breathe with cosmic patience across spans of time we can barely comprehend. Many red giant stars expand and contract in regular pulsation cycles lasting months or years, their luminosity rising and falling like the chest of a sleeping universe. Mira, whose name means wonderful in Latin, brightens and dims by a factor of 1,500 over 332 days as its outer layers swell and shrink by tens of millions of kilometers. These stellar respirations stem from imbalances between gravitational compression and radiation pressure, creating waves that propagate through the star's structure. Such pulsations allow astronomers to measure cosmic distances with precision, as the period of variation correlates directly with absolute brightness. For billions of years, these giants have marked time with their rhythmic breathing, like cosmic metronomes counting beats too slow for human perception to recognize as music. Gravity's embrace weakens with profound mathematical elegance as bodies move apart. The tidal forces between celestial bodies decrease with the cube of the distance between them, creating a rapid diminishment of influence across space. Double the separation, and tidal effect drops to just 1/8 its previous strength. This principle explains why the moon raises stronger tides on Earth than the more massive but distant Sun. The same law governs the gravitational sculpting of planetary rings, the synchronization of rotation between partners in binary systems, and the stretching of matter falling into black holes. The equation itself, a simple inverse cube relation, seems almost too elegant for the complex phenomena it creates across the cosmos. Throughout the universe, this mathematical relationship silently orchestrates a gravitational symphony played across billions of worlds. Beyond Neptune's orbit, thousands of worlds drift in timeless procession. Some dwarf planets maintain stable orbits in the Kuiper Belt for billions of years without disturbance, following paths that have changed little since the solar system's youth. Makemake completes one orbit every 310 Earth years, its surface covered in frozen methane that gives it a reddish tint. Haumea rotates so rapidly that its shape has distorted into an elongated ellipsoid, completing one turn every 3.9 hours. These distant worlds occupy a region where the sun appears as merely the brightest star, providing little warmth or light. Their surfaces remain essentially unchanged for eons, witnessing the slow evolution of the inner planets from afar. Time itself seems different in these outer realms, where orbits are measured in centuries and surface features may persist unchanged for the entire history of Earth's living beings. A perfect measure of stellar energy bathes our world in life-giving radiation. The solar constant at Earth's distance measures 1,361 watts per square meter on average, remaining remarkably stable over human history. Despite the sun's occasional flares and cycles, this flow of energy has varied by less than 0.1% during recorded measurements, providing Earth with the consistent input needed for climate stability. Every square meter of our upper atmosphere receives energy equivalent to a microwave oven operating continuously. Yet, atmospheric filtering and our planet's rotation distribute this power into the gentle warming that enables life. Slight changes in this constant over geological time have driven ice ages and warm periods. The steadiness of this invisible river of energy provides the constant foundation upon which Earth's complex systems have evolved and continue to function. Galaxies rarely travel alone through the vastness of cosmic night. Many exist in groups or clusters bound together by gravitational forces across millions of light years, creating cosmic neighborhoods that drift through space as unified structures. Our own Milky Way belongs to the local group, containing over 54 galaxies spanning 10 million light-years. The largest galaxy clusters may contain thousands of members, their combined mass bending space-time enough to act as gravitational lenses. Despite their collective nature, the distances between member galaxies remain immense, millions of light-years of mostly empty space. These galactic communities formed in the universe's youth as slide-over densities in the cosmic web gradually drew matter together over billions of years. Like villages scattered across an infinite landscape, these clusters provide structure to the universe's largest scales. Our galaxy turns with a patience that makes mountains seem ephemeral by comparison. The rotational velocity of the Milky Way's spiral arms reaches approximately 220 kilometers per second, carrying our solar system in its cosmic carousel. Despite this incredible speed, nearly 1 million kilometers per hour, the galaxy's vast size means that one complete revolution takes 225 million years. The spiral arms themselves are not solid structures, but density waves that propagate through the galactic disk like ripples on water, triggering star formation as they compress nebular clouds in their passage. Stars flow through these arms rather than remaining fixed within them, like water molecules passing through an ocean wave. The entire pattern slowly evolves over billions of years, making our current view of the galaxy merely a single frame in a cosmic film, too long for human comprehension. Delicate atmospheres persist against the vacuum of space for spans of time beyond imagination. Some planetary atmospheres have maintained stable compositions for billions of years, preserving their chemical balances against forces that would disperse them. Mars once held a thicker atmosphere that gradually leaked into space over eons, while Venus has retained its dense carbon dioxide envelope since the solar system's early days. Earth's atmosphere has evolved through biological processes, yet maintained the right conditions for continuous life for at least 3.5 billion years. The persistence of these gaseous envelopes depends on a careful balance between a planet's mass, magnetic field strength, and distance from its star. Each breath we take connects us to an atmospheric legacy that extends back to Earth's formation. Nitrogen molecules that may have cycled through countless organisms before reaching our lungs. Distance reveals itself through the subtle shifting of stellar perspective. The parallax method allows astronomers to measure stellar distances up to several hundred light-years by observing the apparent movement of nearby stars against the background of more distant ones as Earth orbits the Sun. This technique, first successfully applied in 1838 to measure the distance to 61 Cygni, reveals that even the closest stars are separated from us by trillions of kilometers. The slight angular shifts, often less than 1 arcsecond, require precise measurements, yet provide the foundation for cosmic distance calculations. This method operates on the same principle as human depth perception, with Earth's orbit substituting for the separation between our eyes. Through this mathematical relationship between observed angle and actual distance, we have mapped our stellar neighborhood with growing precision, extending our spatial understanding far beyond what our ancestors could have imagined. Families of stone share silent histories in the space between planets. Many asteroid families share similar orbital characteristics, indicating common origins from larger parent bodies that fragmented in ancient collisions. The Flora family contains over 800 members following similar paths, all likely pieces of a single asteroid shattered more than 100 million years ago. Spectroscopic analysis reveals matching compositions within families, confirming their shared heritage. These cosmic siblings continue their orbital journeys in proximity to one another, their paths a record of the violent event that created them. The largest such groups contain thousands of members ranging from kilometer-sized bodies to countless pebbles too small to detect individually. Each family preserves a moment of cosmic violence frozen in time, their continued association a reminder that even in the emptiness of space, relationships persist across astronomical timescales. Invisible scaffolding gives structure to the visible universe. The cosmic web consists of vast filaments of dark matter connecting galaxy clusters across the universe, creating an enormous network that spans billions of light years. This unseen architecture, detected primarily through its gravitational effects, guides the formation and evolution of galaxies along its threads. Computer simulations and observational evidence reveal that approximately 85% of the universe's matter exists in this invisible form, neither emitting nor absorbing light. Galaxies cluster preferentially along these dark matter highways, forming a pattern reminiscent of neurons in a cosmic brain. The largest structures in the universe follow this distribution, with enormous voids between the filaments where few galaxies exist. The visible stars and galaxies we observe are merely luminous tracers of a much larger reality that remains hidden from direct observation. Beneath frozen crusts, hidden oceans whisper of possibility. Some tidally heated moons maintain subsurface oceans for billions of years beneath icy surfaces, warmed by gravitational flexing as they orbit massive planets. Europa, circling Jupiter, harbors more liquid water than all of Earth's oceans combined. Its global sea protected from space by a shell of ice several kilometers thick. Enceladus reveals its hidden ocean through geysers erupting from its south pole, spraying water vapor into space as it orbits Saturn. These liquid realms have existed potentially since the formation of the solar system, providing stable environments where complex chemistry could evolve in isolation from the surface. The gentle tidal heating that maintains these oceans operates with perfect consistency, creating what might be the most stable environments in our solar system. Beneath billions of tons of ice, water moves in perpetual currents untouched by human eyes. The visible surface of our sun maintains a delicate balance of immense forces. The photosphere of the sun maintains an average temperature of 5,778 Kelvin across its surface, creating the yellow-white light that defines our days. This apparent surface is not solid, but a layer of plasma, where energy from the core finally becomes visible after a journey lasting thousands of years. The granulated pattern visible through telescopes reveals convection cells where hotter material rises and cooler plasma sinks, each granule spanning approximately 1,000 kilometers. Magnetic fields create darker regions called sunspots, where temperatures drop to about 4,000 Kelvin, still hot enough to glow brightly if they could be isolated from the surrounding photosphere. This luminous boundary between the sun's interior and outer space has remained stable for billions of years, varying by less than 1% in temperature despite the complex processes occurring beneath it. The death shrouds of stars drift outward in ghostly symmetry. Many planetary nebulae retain their distinctive shapes for thousands of years as they expand into space, preserving the final moments of stellar evolution in slowly fading displays of color and form. The Ring Nebula has maintained its characteristic annular structure for approximately 7,000 years as it expands at 20 to 30 kilometers per second. These formations begin when aging stars shed their outer layers, allowing ultraviolet radiation from the exposed core to ionize the expanding gas. The diverse forms, butterflies, hourglasses, rings, result from the interaction between stellar winds and surrounding material. Though they may appear static in human time frames, these nebulae continuously expand and fade, destined to disappear into the interstellar medium within 50,000 years of their creation. Each one marks a transient moment of transformation, where a star that burned for billions of years releases its substance back to the cosmos. Beyond the visible disk of our galaxy extends a spherical cloud of ancient mysteries. The galactic halo extends far beyond the Milky Way's spiral arms, containing ancient stars and dark matter in a roughly spherical distribution that reaches more than 100,000 light-years from the galactic center. The visible stellar component consists primarily of globular clusters and individual stars formed in the universe's youth, over 12 billion years ago. These ancient stellar populations contain little of the heavier elements common in younger stars, telling stories of a different era in cosmic evolution. The majority of the halo's mass exists as dark matter, detectable only through its gravitational effects on visible structures. This extended envelope surrounds the familiar spiral disk like an invisible atmosphere, connecting our galaxy to the larger cosmic web. The halo's stars move in largely random orbits, unlike the organized rotation of the disk, their paths reflecting the chaotic conditions of the early universe. Some stones in space have found eternal companions in the void. Some binary asteroids orbit each other in stable configurations for millions of years, locked together by mutual gravitational attraction as they travel around the Sun. The asteroid Antiope consists of two similarly sized bodies, approximately 80 kilometers in diameter, orbiting their common center of mass every 16.5 hours at a separation of about 170 kilometers. Nearly 1/6 of asteroids larger than 200 meters have companions, creating miniature solar systems that have remained stable since their formation or subsequent collision. The paths of these paired objects are governed by the same physical laws that direct planets around stars, operating on a much smaller scale. Some systems contain 3 or more objects in mutual orbit, creating complex gravitational choreography that has continued uninterrupted for eons. These silent partnerships will likely endure until the Sun itself transforms in the distant future. Above the glowing surface of our star lies a realm of translucent fire. The chromosphere of the Sun extends approximately 2,000 kilometers above the photosphere, a layer where temperatures paradoxically rise with altitude rather than fall. This reddish region becomes visible during solar eclipses when the Moon covers the brighter photosphere, appearing as a thin crimson ring around the obscured disk. Within this layer, temperatures climb from 6,000 to 20,000 Kelvin through processes not fully understood, creating a transition between the visible surface and the much hotter corona beyond. Spicules, jet-like structures resembling grass blades, rise and fall through this region, each lasting just a few minutes, but appearing continuously across the solar surface. The chromosphere absorbs specific wavelengths of light coming from below while emitting its own spectrum, creating the colored flash seen momentarily during eclipses. This threshold between worlds shapes the light that ultimately reaches Earth, invisible except during rare moments of cosmic alignment. Stars begin as whispers in clouds that span light years. Many star-forming regions contain protostars that take millions of years to reach the main sequence, gradually condensing from nebular material under gravity's patient hand. The earliest stages remain hidden within dense molecular clouds, detectable primarily in infrared wavelengths that penetrate the surrounding dust. A typical solar mass protostar spends approximately 100,000 years gathering material before initiating the nuclear fusion that defines true stellar status. During this formative period, the embryonic star grows through accretion while shedding angular momentum through powerful bipolar outflows that can extend for light years into space. Temperature and pressure slowly build in the core until hydrogen fusion ignites, bringing stability that may last billions of years. What appears as a sudden birth from our perspective is actually a gradual awakening spanning millions of orbits of Earth around the Sun. Energy dances across the Sun's surface in continuous acts of magnetic reunion. Magnetic reconnection events on the Sun occur continuously, releasing energy into the solar atmosphere as magnetic field lines break and rejoin in new configurations. These events range from tiny nanoflares to massive explosions visible from Earth, each converting magnetic energy into heat, light, and kinetic energy. The process begins when oppositely directed magnetic fields are brought together, creating unstable boundaries where the field lines can break and reconfigure. During major reconnection events, particles may be accelerated to nearly the speed of light while plasma is heated to millions of degrees. The constant occurrence of these events helps explain why the Sun's outer atmosphere reaches temperatures hundreds of times hotter than its surface. Like cosmic lightning that never ceases, these magnetic realignments have continued since the Sun's formation, releasing their energy in patterns too complex to fully predict, yet too ordered to be random. Jupiter shares its orbit with ancient companions, captured in perfect balance. Some Trojan asteroids share Jupiter's orbit, remaining in stable positions 60 degrees ahead of and behind the massive planet for billions of years. These cosmic followers occupy regions called Lagrange points, where gravitational forces from Jupiter and the Sun create pockets of stability. More than 7,000 such objects have been catalogued, with estimates suggesting over 1 million larger than 1 kilometer exist in these regions. The leading group is named for Greek warriors of the Trojan War, while the trailing group bears the names of their Trojan opponents, a cosmic reenactment of ancient human stories. These primordial objects likely formed elsewhere in the solar system before being captured in their current positions during Jupiter's early migration. Protected by the perfect gravitational balance of their locations, they have witnessed the entire history of Earth from their distant vantage points. Aging stars exhale their substance into the void with quiet generosity. The stellar wind from red giant stars carries mass into interstellar space at rates measured in solar masses per year, enriching the cosmos with elements forged in stellar cores. Our Sun will eventually shed approximately half its mass through this process, creating an expanding shell of material that may extend for light years. These winds flow at tens of kilometers per second, slower than those from hot young stars, but carrying far more mass. The material ejected contains carbon, nitrogen, and oxygen, crucial for forming planets and potentially life. Betelgeuse currently loses enough mass each year to form an Earth-sized planet, a process that has continued for thousands of years. The universe itself breathes through these stellar exhalations, circulating elements from stellar interiors out into the void where they will eventually form new stars, planets, and perhaps living beings. Worlds wander from their birthplaces in journeys spanning eons. Many planetary systems show evidence of migration, with planets slowly changing their orbital distances due to interactions with protoplanetary disks or other worlds. Jupiter likely formed farther from the Sun before moving inward and then outward to its current position, its gravitational influence helping shape the entire solar system during this journey. This process occurs gradually over millions of years as planets exchange angular momentum with surrounding material or neighboring bodies. Hot Jupiters, gas giants orbiting extremely close to their stars, represent extreme examples of migration, having formed in cooler regions before spiraling inward. The current arrangement of planets in our solar system represents just one frame in a slow-motion film of orbital evolution that began 4.6 billion years ago and continues today. The night sky we observe reflects not static design, but the current moment in a choreography of worlds still underway. Above our star's surface extends an invisible kingdom of extraordinary heat. The corona of the Sun extends millions of kilometers into space with temperatures exceeding 1 million Kelvin, creating a ghostly halo visible only during total solar eclipses or through specialized instruments. This outermost layer of the solar atmosphere transitions seamlessly into the solar wind that extends throughout the solar system. The extreme temperature, hundreds of times hotter than the Sun's surface, represents one of solar physics' greatest mysteries, likely explained through magnetic heating mechanisms still being investigated. Structurally, the corona contains streamers, loops, and holes shaped by magnetic fields emerging from deeper layers, constantly changing yet maintaining overall stability. Despite its high temperature, the corona's extraordinarily low density means it contains little total heat energy and would feel cold to human touch if one could somehow survive the other conditions. Through this ethereal region, Our star connects directly to Earth's environment across 150 million kilometers of space. From the centers of distant galaxies extend rivers of energy flowing across cosmic voids. Some quasar jets extend for hundreds of thousands of light years, maintaining their structure across vast distances as they carry plasma away from supermassive black holes at nearly the speed of light. The longest such jet, associated with quasar PKS 0637752, stretches over 1 million light-years through intergalactic space. These enormous structures form when magnetic fields channel some of the energy from matter falling toward a black hole into narrow beams of particles and radiation. Despite crossing distances larger than entire galaxies, these jets often maintain remarkably straight paths, their material held together by internal magnetic fields. The energy carried by a single powerful jet over its lifetime could outshine an entire galaxy of stars. Yet this extraordinary output may continue steadily for millions of years. Like cosmic fountains extending from invisible sources, these jets connect the smallest scales, the vicinity of black holes, with the largest structures in the universe. Each planet creates its own sphere of gravitational dominance. The Hill sphere of a planet defines the region where its gravity dominates over the star's gravitational influence, determining the volume within which moons can maintain stable orbits. Earth's Hill sphere extends approximately 1.5 million kilometers in all directions, about 4 times the Earth-Moon distance. Beyond this invisible boundary, the Sun's gravity would gradually pull any satellite away from planetary orbit. Jupiter's much larger sphere allows it to maintain dozens of moons at considerable distances. This gravitational territory scales with a planet's mass and distance from its star, creating unique orbital environments around each world. The concept extends beyond our solar system, defining the regions where exoplanets can hold their own satellite systems. These spheres of influence overlap at precise points where gravitational forces balance perfectly, creating pathways between planetary systems used by spacecraft to minimize fuel consumption during interplanetary journeys. Traces of ancient comets create annual light shows in Earth's night sky. Many meteoroid streams follow predictable orbits, creating annual meteor showers visible from Earth when our planet passes through these rivers of dust. The Perseid meteor shower occurs each August as Earth intersects debris left by Comet Swift-Tuttle along its 133-year orbit around the Sun. Some streams have spread so widely that they create meteor showers lasting days or weeks, their particles distributed along the entire orbital path of the parent comet. The oldest recognized showers have been observed for thousands of years, mentioned in ancient Chinese, Greek, and Arab astronomical texts. Each visible meteor represents a dust grain the size of a sand particle, burning up in Earth's atmosphere at heights of about 80 kilometers. The predictable recurrence of these cosmic encounters connected human timekeeping to celestial cycles long before their true nature was understood. Our galaxy forms a disk of light suspended in darkness. The galactic disk of the Milky Way measures approximately 1,000 light-years thick and 100,000 light-years in diameter, creating the distinctive spiral structure visible in similar galaxies throughout the universe. This flattened shape resulted from angular momentum conservation as the protogalactic cloud collapsed more than 13 billion years ago. The thickness represents less than 1% of the diameter, making our galaxy proportionally thinner than a compact disk. Within this relatively narrow space, exists most of the Milky Way's visible matter, hundreds of billions of stars, thousands of nebulae, and countless planets. Our solar system resides about 27,000 light-years from the galactic center in a relatively sparse region between major spiral arms. The disk's rotation varies with distance from the center, completing one revolution every 250 million years at our position. Like a vast cosmic carousel, this structure has maintained its general form while slowly evolving for billions of years. Delicate forces shape the architecture of planetary rings. Some planetary rings maintain gaps created by the gravitational influence of shepherd moons, small satellites whose orbits stabilize ring structures through regular gravitational interactions. The Enski gap in Saturn's A-ring spans 325 kilometers and is maintained by the small moon Pan, which clears its orbital path of ring particles through repeated gravitational encounters. These interactions create complex patterns, including waves, braids, and clumps that evolve over periods ranging from days to decades. Despite their apparent stability, ring systems represent transitional structures that may disperse over millions of years or be replenished by material from disintegrating moons or captured comets. The subtle gravitational dance between tiny moons and countless ring particles demonstrates how complex order can emerge from simple physical principles operating across vast numbers of independent objects. Each ring system becomes a natural laboratory for gravitational dynamics, visible from Earth through even modest telescopes. At the heart of every star burns a fusion reactor of perfect precision. The nuclear fusion in stellar cores converts hydrogen to helium at rates determined by temperature and pressure, releasing energy that sustains stars for billions of years. In our Sun, approximately 600 million tons of hydrogen fuse into helium each second, yet this represents just 0.037% of its total mass annually. The process requires temperatures exceeding 15 million Kelvin and densities 150 times that of water to overcome the mutual repulsion of positively charged protons. The energy released travels outward through the stellar interior, taking between 10,000 and 170,000 years to reach the surface before escaping as light. Despite the enormous energy production, most stars maintain remarkable stability through the perfect balance between gravitational compression and radiation pressure. This delicate equilibrium allows stars like our Sun to maintain nearly constant output for billions of years, providing the stable energy essential for life. Stellar siblings gradually drift apart as time dissolves their birthplace bonds. Many open star clusters gradually disperse over hundreds of millions of years as members drift apart, their mutual gravitational attraction insufficient to counter the tidal forces from the galaxy. The Hyades cluster in Taurus, visible to the naked eye, has already lost most of its original stars during its 625 million year history. Over time, differences in orbital velocity around the galactic center stretch the cluster into an elongated structure before its stars merge completely with the galactic background population. The Sun itself likely formed in such a cluster, its siblings now scattered throughout the galaxy, identifiable only through chemical composition analysis. This slow dissolution represents the final chapter in the shared history of stars born from the same molecular cloud. Though they journey apart, these stars carry identical elemental signatures, a kind of genetic marker, recording their common origin in a now vanished stellar nursery. Our moon reveals slightly different faces through a cosmic optical illusion. The libration of the moon allows Earth-based observers to see approximately 59% of the lunar surface over time, despite the moon keeping the same hemisphere perpetually facing Earth. This apparent wobbling occurs because the Moon's orbit isn't perfectly circular, and its axis is slightly tilted, allowing observers to peer around its edges from different angles throughout its monthly cycle. The effect was first documented by Galileo in 1637, though ancient astronomers had noticed the shifting visibility of features near the lunar limb. Over time, a patient observer can glimpse regions beyond the Moon's average face, including portions of the lunar far side that would otherwise remain forever hidden. This gentle rocking motion has continued since the Moon achieved tidal locking billions of years ago, a subtle oscillation in an otherwise perfect synchronization between rotation and orbit. The deaths of stars fertilize space with ingredients for new worlds. Some supernova remnants expand into the interstellar medium for thousands of years, enriching it with heavy elements forged in their progenitor stars' cores, and during the explosion itself. The Crab Nebula, resulting from a supernova observed in 1054 CE, continues expanding at over 1,500 kilometers per second, its shell now spanning 11 light-years. Elements essential for life, carbon, nitrogen, oxygen, and materials crucial for terrestrial planets, silicon, iron, nickel, can only exist in abundance through stellar nucleosynthesis and distribution via supernovae. Every atom of iron in human blood was created in a star that exploded billions of years ago. These remnants gradually merge with the interstellar medium, their distinctive structures fading over approximately 100,000 years as their energy dissipates. The elements they release, however, remain available for incorporation into new stars, planets, and eventually living beings. A bridge of dust connects Earth to the broader cosmos. The zodiacal light visible before dawn results from sunlight scattered by interplanetary dust particles, creating a faint, triangular glow, extending upward from the horizon along the ecliptic plane. These microscopic particles, primarily debris from asteroid collisions and comet passages, orbit the Sun in the same plane as the planets, creating a lens-shaped cloud that permeates the inner solar system. The phenomenon appears most prominently in spring evenings and autumn mornings at tropical latitudes, where the ecliptic rises steeply from the horizon. This dust continuously replenishes as new material enters the system, while older particles gradually spiral toward the Sun due to the Poynting-Robertson effect or are ejected by radiation pressure. The glow has been observed and recorded since antiquity, appearing in ancient texts from various cultures, though its true nature remained unknown until the 19th century. What appears as a simple twilight glow reveals our direct connection to the cosmic processes that distribute matter throughout our planetary neighborhood. Worlds unlike any in our solar system populate the galaxy in unexpected abundance. Many exoplanet systems contain super-Earths with masses between Earth and Neptune that orbit close to their stars, despite no such planets existing in our solar system. These worlds, typically 2 to 10 times Earth's mass, represent the most common type of known exoplanet, suggesting our solar system's architecture may be somewhat unusual. Some complete their orbits in just days or weeks, experiencing intense stellar radiation that creates exotic conditions unlike anything in our planetary neighborhood. The existence of these planets challenges traditional formation theories, suggesting complex migration patterns or different formation mechanisms than those that shaped our system. Despite their prevalence, we have no direct observations of their surface conditions or atmospheres, leaving their true nature mysterious. The discovery of these unexpected worlds reminds us that the universe's creativity exceeds our imagination, producing planetary systems more diverse than we could have predicted from our single example. The gentle boundary between day and night travels across every world in silent passage. The Terminator line on planets and moons separates light from darkness, slowly moving as each body rotates, bringing dawn to some regions while drawing twilight's curtain across others. On Earth, this dividing line travels at over 1,000 miles per hour at the equator. Yet we experience it as the gradual softening of light at dusk, the slow brightening at dawn. You've crossed this boundary countless times in your life, perhaps watching shadows lengthen as the sun dips below the horizon, or feeling morning's first warmth on your face. Every photograph taken from space shows this curved line separating illuminated terrain from shadow, a reminder that even in our technological world we still live by the rhythm of a turning planet. In this daily transition between light and darkness, we find a universal experience shared by every being that has ever watched a sunset. Beneath skies no human has yet seen, storms rage with breathtaking power and beauty. Some brown dwarf atmospheres contain weather systems with wind speeds reaching hundreds of kilometers per hour, creating bands and swirls of cloud that dwarf Earth's most powerful hurricanes. These failed stars, too large to be planets but too small to sustain fusion, experience weather patterns driven by their own internal heat rather than apparent star's energy. If you could somehow stand on their surfaces, you would witness clouds of iron droplets and silicate dust swirling in alien tempests. These distant storms remind us of our own weather, how we've sheltered from rain, chased after snowflakes, or felt the wind's touch against our skin. While these faraway worlds experience weather beyond our imagination, they connect us to the universal experience of looking upward at changing skies, of finding comfort in the familiar patterns of atmospheric flows that touch all worlds with air. At the heart of our galaxy waits a center we cannot see but forever orbit. The galactic center of the Milky Way lies approximately 26,000 light-years from our solar system, hidden behind dense clouds of interstellar dust that block visible light. Around this center, containing a supermassive black hole and millions of stars, crowded into a region smaller than the distance between our sun and its nearest neighbor, our solar system completes one orbit every 225 million years. Though invisible to our eyes, radio telescopes have mapped this region in exquisite detail, revealing a place of extraordinary energy and complexity. You are part of this grand orbital dance, riding on a planet that follows the sun as it traces its path around this distant core. When you look toward the constellation Sagittarius on a summer night, you're gazing toward home, the center around which all our stellar journeys revolve. In the emptiness between worlds, matter changes in ways impossible on Earth. Many volatile compounds sublimate directly from solid to gas phase in the vacuum of space, skipping the liquid state entirely. Ice on an airless moon doesn't melt into puddles, but transforms into vapor that either escapes into space or redeposits elsewhere as frost. This process shapes the ethereal cometary tales that have inspired wonder throughout human history, as ices vaporize under the sun's warmth. Your own experience of matter, the familiar phases of water as ice, liquid, and steam, is shaped by Earth's atmospheric pressure, a condition rare in the cosmos. Yet in this difference lies connection. The same physics that creates a comet's glowing tail also forms the morning frost on your window, the dew that sparkles on grass at dawn. The rules that govern matter bind us to the stars through shared patterns, whether here on Earth or in the distant reaches of space. Every world has its boundary where closeness becomes too intimate for survival. The Roche limit determines the minimum distance at which a moon can orbit without being torn apart by tidal forces, creating a mathematical boundary where gravity's embrace becomes destruction. Within this invisible line, the difference in gravitational pull between a moon's near and far sides exceeds the moon's own gravitational binding. Saturn's rings exist because potential moons ventured too close and were pulled apart into billions of particles, each finding its own orbit. This cosmic principle mirrors something we understand intuitively in our own lives: the delicate balance between closeness and independence, between holding tight and letting go. Just as every relationship has its own unique equilibrium, every planetary body creates its own gravitational boundary, where coming closer means transformation rather than continued existence. In both cosmic and human relationships, there is wisdom in respecting these natural boundaries. The ghosts of vanished galaxies drift through our night sky in ribbons of ancient stars. Some stellar streams result from disrupted globular clusters or dwarf galaxies stretched across the sky by the Milky Way's tidal forces, creating rivers of stars that may span thousands of light years. The Sagittarius stream contains stars from a small galaxy that began merging with our own billions of years ago. Its structure now wrapped multiple times around the Milky Way like a cosmic scarf. You might unknowingly gaze upon these stars on a clear night, seeing them as random points of light rather than the remnants of a cosmic collision. These stellar streams remind us how even in dissolution there is beauty. Scattered stars still move together in cosmic remembrance of their shared origin. Our own lives mirror this pattern, as connections with people and places remain, even when separated by time and distance, invisibly shaping our journeys through shared history and memory. Deep within our sun lies a realm where light itself slows to a crawl. The radiative zone of the sun extends from the core to approximately 70% of the solar radius, a region where photons bounce from particle to particle in a zigzag journey that may take 100,000 years to complete. In this dense plasma layer, energy moves outward through radiation rather than convection, with each light particle traveling less than a centimeter before being absorbed and re-emitted in a random direction. The sunlight warming your skin began its journey when our ancestors were still painting cave walls, patiently working its way outward before finally racing across space to reach you in just 8 minutes. This patient progression of energy mirrors our own slow journeys of transformation. How wisdom often comes not in straight lines, but through countless interactions, redirections, and patient persistence. The light that nurtures life on Earth teaches us that even the longest journeys eventually reach their destination. The air you breathe shares its layered nature with worlds throughout our solar system. Many planetary atmospheres exhibit distinct layers with different temperatures and chemical compositions, creating invisible boundaries in the skies of Earth, Venus, Mars, and the giant planets. Our own atmosphere transitions from the troposphere where weather occurs, through the stratosphere where ozone protects us, to the thermosphere where auroras dance. Each breath you take connects you to this complex structure that has evolved over billions of years, filtering sunlight and moderating temperature to create conditions perfect for life. When you look up at blue sky or evening clouds, you're seeing just the innermost layer of a sophisticated system that wraps around our entire world. These atmospheric layers remind us that protection often comes in stages, that transitions create buffers between extremes, and that the boundaries between us and space are gentler than they first appear. The dance of planets follows rhythms that connect them across empty space. The synodic period of planets determines how often they appear in the same position relative to Earth, creating cycles of celestial meetings that repeat with mathematical precision. Venus meets Earth in the same configuration every 584 days, while Jupiter returns to the same apparent position approximately every 399 days. Ancient cultures tracked these cycles, finding in them patterns for planting, religious ceremonies, and navigation. When you notice a bright planet in the evening sky, you're participating in an observation that spans human history. The recognition of cosmic patterns that connect moments across time. These planetary rhythms remind us that separation in space doesn't prevent relationship, that distant objects maintain connections through shared orbits and mutual influence. Like friends whose paths cross at predictable intervals, the planets maintain their relationships through mathematically perfect reunions spread across years. Some stars share their substance in the ultimate cosmic embrace. Contact binary stars share a common envelope while maintaining separate cores, their stellar atmospheres touching and exchanging material in a perpetual kiss. These pairs rotate around their center of mass every few hours to days, their mutual gravitational attraction pulling their outer layers into teardrop shapes. Eventually, many will merge completely to form a single star. The closest such system to Earth, KIC 9832227, may merge within our lifetime, temporarily brightening thousands of times. There's something profoundly moving about these stellar unions. How two separate entities can come so close that their boundaries blur, while each core maintains its identity. They mirror the deepest connections we form with others, where closeness doesn't erase individuality, but creates something greater than either could be alone. In their patient orbits, these stars remind us that sharing can be a form of preservation rather than loss. Beneath the sun's visible face lies a realm of constant motion and energy. The convective zone of the sun extends from 70% of the radius to the photosphere, a region where energy moves through the physical circulation of plasma rather than radiation. Here, superheated material rises to the surface before cooling and sinking again, creating cell-like patterns visible as granulation on the sun's surface. Each granule spans about 1,500 kilometers, approximately the distance from New York to Kansas City, yet from Earth appears as merely a speck of texture on the solar disk. This constant churn delivers energy from the sun's depths to its surface, where it radiates into space and ultimately nurtures life on Earth. The warmth you feel on your skin on a summer day comes from this perpetual circulation, connecting you directly to the inner workings of our star. Like blood moving through a body, this convection maintains the sun's life-giving presence through endless cycles of rising and falling. Around young stars, new worlds take shape from cosmic dust and patient gravity. Many protoplanetary disks around young stars contain gaps that may indicate forming planets, their gravitational influence clearing paths through the surrounding material like stones parting a stream. These planet-forming regions have been photographed with increasing clarity, revealing the birthplaces of worlds that may someday harbor their own forms of life. The process that shaped our Earth continues throughout the galaxy, with each new star likely accompanied by planets in various stages of formation. When you look at the ground beneath your feet, you're standing on the result of this process. Matter that once drifted around our young sun before gathering into the planet that became our home. These distant disks with their forming worlds connect us to our own cosmic beginnings, to the patient accumulation of dust and rock that, over millions of years, became a world capable of wondering about its origins. There is a limit to how massive a dying star can remain without collapsing completely. The Chandrasekhar limit sets the maximum mass for white dwarf stars at approximately 1.4 solar masses, a boundary where electron degeneracy pressure can no longer resist gravity's pull. This threshold, named for the Indian-American astrophysicist who first calculated it, determines whether a star's remains will cool slowly as a white dwarf or explode as a supernova before collapsing into a neutron star. When you gaze at the evening star Sirius, its tiny white dwarf companion Sirius B hovers just below this limit, its mass compressed into a sphere no larger than Earth. The mathematics that define this stellar boundary remind us that even in the cosmos, there are limits to what can be sustained, points beyond which transformation becomes inevitable. In our own lives, we too encounter thresholds where gentle change gives way to profound transformation, where holding on becomes less possible than becoming something entirely new. Some moons follow paths that defy the orderly patterns of our solar system. Irregular moons follow highly elliptical, inclined orbits around their parent planets, often circling in the opposite direction from the planet's rotation. These cosmic wanderers were likely captured from passing asteroids or comets, rather than forming alongside their planets, their unusual paths preserving the memory of ancient encounters. Neptune's moon Triton travels backward compared to the planet's spin, gradually spiraling closer until, millions of years from now, it will either break apart or impact the planet it orbits. These wayward moons remind us that not all journeys follow predictable paths, that sometimes the most interesting stories come from objects that travel against the prevailing flow. Your own life may include unexpected turns and detours that ultimately became central to your story. Like these captured moons, our unplanned encounters often become defining features of our existence. A shield of invisible energy wraps around our planet, protecting all life below. The magnetosphere of Earth deflects most solar wind particles, protecting the atmosphere from erosion that would otherwise gradually strip away the air we breathe. Created by the movement of molten iron in Earth's outer core, this magnetic bubble extends tens of thousands of kilometers into space on the sunward side, before stretching into a long tail in the opposite direction. When charged particles from the sun do penetrate this barrier, they create the aurora, curtains of light that dance near the poles. Each breath you take exists because of this protective field that has surrounded Earth for billions of years. The next time you see a compass needle align with magnetic north, remember that you're detecting the same force field that has made Earth habitable for eons. In this invisible protection, we find a perfect metaphor for the unseen forces that sustain and protect life in all its forms. Throughout the galaxy, stellar families maintain their connections across billions of years. Many multiple star systems maintain stable hierarchical orbits for billions of years, with stars arranged in nested pairs that preserve their gravitational balance against the chaos of space. Alpha Centauri, our nearest stellar neighbor, consists of 3 stars, 2 sun-like stars orbiting each other every 80 years, with a distant red dwarf, Proxima Centauri, circling the pair every 550,000 years. When you look up at night, many points of light you perceive as single stars are actually multiple systems, their components too close to distinguish without a telescope. These stellar arrangements mirror the complexity of human relationships, how we form bonds of varying closeness, how some connections remain distant yet enduring, while others involve daily interaction. The stability of these systems over cosmic timescales offers quiet testimony to how balance and mutual influence can create lasting harmony, whether between massive stars or between people sharing their lives. A boundary of temperature shapes where different worlds can form. The frost line in protoplanetary disks marks the distance where water ice can condense from the gas phase, creating a division between rocky worlds closer to the star and gas-rich worlds farther away. In our solar system, this line fell between the current orbits of Mars and Jupiter, explaining the dramatic difference between the inner terrestrial planets and the outer gas giants. This temperature gradient influenced the chemistry of each forming world, determining which elements remained and which were lost to space. Your own body, composed largely of water and carbon compounds that could only have formed beyond this boundary, contains elements that had to be delivered to early Earth by comets and asteroids from cooler regions. The warmth of your being depends on materials that could only exist in the cold of space, a paradox that connects your physical existence to the temperature gradients of our early solar system. Around the remains of explosive stellar deaths, planets maintain perfect timekeeping. Some pulsar planets orbit neutron stars in extremely regular periods, measured to nanosecond precision, circling these collapsed stellar cores like cosmic clockwork. The first exoplanets ever discovered were found around pulsar PSR B11257+12 in 1992, revealing a system of planets that survived or formed after their star's violent supernova. These worlds orbit a star no larger than a city but containing more mass than our Sun, compressed into a sphere spinning hundreds of times per second. When you check the time on your watch or phone, you're participating in humanity's ancient quest to measure the passage of moments, a quest that finds its ultimate expression in these pulsar systems, where orbital periods can be measured more precisely than any clock on Earth. In these distant, radiation-bathed worlds orbiting stellar remnants, the universe demonstrates that order can emerge even from catastrophic transformation. Our galaxy holds a mystery in its rotation, a pattern that defies simple explanation. The galactic rotation curve shows that orbital velocities remain constant at large distances from the galactic center, rather than decreasing as would be expected from the visible mass distribution. Stars near the edge of the Milky Way move at nearly the same speed as those much closer to the center, suggesting the presence of vast amounts of invisible matter extending far beyond the visible disk. This observation provides the strongest evidence for dark matter, an unseen substance that appears to comprise about 85% of all matter in the universe. When you look at the Milky Way stretching across a dark sky, remember that what you see represents only a fraction of what's there, like the depths of an ocean glimpsed from the surface, or the thoughts behind a loved one's eyes. The most profound aspects of existence often remain invisible, yet make themselves known through their effects on what we can observe. Beyond Neptune, icy worlds follow paths of extraordinary patience through the outer darkness. Many trans-Neptunian objects follow highly elliptical orbits that take centuries to complete, traveling far from the Sun before gradually returning to the warmer inner regions. Eris, nearly the size of Pluto, takes 559 years to complete a single orbit that carries it between 38 and 98 times Earth's distance from the Sun. These distant travelers move through a realm of perpetual twilight, where our Sun appears as merely the brightest star rather than the blazing disk we know. Their slow journeys remind us of the vastness of time, how some cycles complete within a human lifetime, while others span generations. Like ancient trees that witness centuries of human history, These objects maintain their quiet orbits regardless of the brief dramas unfolding on Earth. Their patient trajectories offer perspective on our hurried lives, connecting us to timescales that extend far beyond our individual existence. At the edge of reality, space bends into a boundary from which nothing returns. The Schwarzschild radius defines the event horizon of black holes based on their mass, creating a spherical point of no return proportional to the amount of matter contained within. For a black hole, with the mass of our Sun, this radius would be just 3 kilometers, while for the supermassive black hole at our galaxy's center, it spans millions of kilometers. Though the mathematics describing this boundary were developed a century ago, the first direct image of a black hole's shadow wasn't captured until 2019. When you feel the pull of gravity keeping you grounded, you're experiencing a gentler version of the same force that creates these cosmic boundaries. Each time you drop an object and watch it fall, you witness the same fundamental interaction that, in its most extreme form, curves space-time itself into a one-way passage. The humble force that shapes your daily experience also creates the universe's most profound thresholds. Some stars experience moments of brilliant transformation between long periods of quietude. Cataclysmic variable stars undergo periodic outbursts that increase their brightness by several magnitudes, temporarily outshining their usual appearance before returning to dormancy. These dramatic changes occur in binary systems, where a white dwarf pulls material from a companion star, accumulating it on its surface, until temperatures and pressures trigger nuclear fusion in a brief, spectacular flash, visible across thousands of light years. After each outburst, the cycle begins again. Accumulation, threshold, brilliance, and return to quiet gathering. You might recognize this pattern from your own life. How periods of seeming stillness often precede moments of insight or transformation. How growth often appears to happen suddenly after long preparation. These stellar cycles remind us that dramatic change and quiet persistence are not opposites, but partners in the rhythm of existence, whether in the life of a star or the journey of a human heart. The region where life as we know it can exist moves outward as stars age and brighten. The habitable zone around stars shifts outward as stellar luminosity increases over billions of years, creating a moving target for the development of life. Our Sun now shines about 30% brighter than it did when Earth formed 4.5 billion years ago, and will continue brightening until, in about 1 billion years, Earth's oceans begin to evaporate. Mars, currently too cold, may enter the habitable zone as the Sun continues to warm, while Earth will eventually become too hot to maintain liquid water on its surface. Life on our planet has adapted to these gradual changes, evolving mechanisms to regulate temperature and maintain habitability, despite the slowly increasing solar output. Your own existence occurs during an ideal window in this long progression, a time when Earth's temperature allows liquid water to flow across its surface, supporting the complex ecosystems that ultimately gave rise to human consciousness. Stars light their cosmic neighborhoods in sequential patterns of creation. Many star formation regions show sequential stellar birth triggered by shockwaves from nearby supernovae, creating generations of stars that ignite one after another, like candles sharing their flame. The pressure from one generation's stellar winds and supernovae compresses neighboring gas clouds, initiating the collapse that leads to new star formation. In the Orion Nebula, astronomers have identified distinct age groups of stars that formed in succession over millions of years, their births connected through this process of triggered formation. When you look at the stars of Orion's sword on a winter night, you're seeing this multi-generational stellar family, with middle-aged stars influencing the birth of their younger neighbors. This cosmic relay of creation mirrors how knowledge and inspiration pass through human generations. How the efforts of those who came before create conditions that spark new beginnings, connecting lives across time through shared influence and transformation. The paths of planets in our neighborhood follow curves of remarkable smoothness. The orbital eccentricity of most planets in our solar system remains below 0.1, indicating nearly circular orbits that vary only slightly from perfect circles. Venus maintains the most circular path with an eccentricity of just 0.07, deviating by less than 1% from a perfect circle in its journey around the Sun. This orbital harmony contributes to the stable climate conditions that have allowed life to flourish on Earth, avoiding the extreme temperature variations that would come with highly elliptical paths. As you move through your daily routines, you're carried along Earth's balanced trajectory, a path neither rushing toward the sun nor straying too far from its life-giving warmth. These gentle cosmic curves have cradled human civilization since its beginning, providing the reliable cycles of seasons and years by which we measure our lives and grow our food. In their mathematical beauty, these orbits offer a model of balance and moderation. Throughout the solar system, moons maintain relationships through mathematical harmony. Many planetary satellites maintain orbital resonances that stabilize their positions for geological timescales, creating patterns where they return to the same relative positions after fixed numbers of orbits. Jupiter's moons, Io, Europa, and Ganymede maintain a precise 4.2.1 resonance, with Io completing 4 orbits for every 2 of Europa and 1 of Ganymede. These relationships are not coincidental, but emerge from the gravitational influence each body exerts on the others, gradually locking them into synchronized patterns. The rhythms created by these resonances affect the moon's internal heating, surface features, and long-term stability. In your own life, you may have experienced how relationships often find their own natural frequencies, how connections with others develop recurring patterns of interaction and mutual influence. Like these moons in their cosmic dance, we too find stability through the resonant patterns we create with those around us. The history of our galaxy can be read in the chemical makeup of its stars. The metallicity of stars correlates with their age, as successive generations contain heavier elements created through stellar nucleosynthesis and supernovae. The oldest stars in our galaxy contain almost exclusively hydrogen and helium, while younger stars like our Sun include substantial amounts of carbon, oxygen, iron, and other elements created in previous stellar generations. Our own bodies contain atoms forged in stars that lived and died before our Sun formed, connecting us directly to this cosmic enrichment process. The calcium in your bones, the iron in your blood, and the carbon in your cells could only exist because earlier stars created these elements and scattered them through space. When you look at the night sky, you're seeing both your cosmic ancestors and your distant cousins. Stars of various ages and compositions, each representing a chapter in the ongoing story of element creation that made your existence possible. The messengers from the solar system's edge are more delicate than they appear. Many cometary nuclei are loose aggregations of ice and rock held together by weak gravitational forces, their structure resembling a rubble pile rather than a solid object. With densities often less than that of water, and compositions that can be up to 80% empty space, these cosmic snowballs could sometimes be crushed in a human hand if brought to Earth's surface intact. Yet these fragile objects have preserved their material largely unchanged since the solar system's formation 4.6 billion years ago, providing a record of the conditions in which our planetary neighborhood formed. When you see a comet's tail stretching across the night sky, you're witnessing the gentle disintegration of one of the solar system's most ancient and vulnerable objects. Their delicate nature reminds us that sometimes the most ephemeral things carry the oldest memories, and that beauty often emerges from fragility rather than strength. The center of our galaxy holds stellar treasures of extraordinary richness. The galactic bulge contains older stars with higher metallicities than those in the galactic halo, creating a concentration of element-rich stars around the Milky Way's core. This region, spanning about 10,000 light-years in diameter, formed early in our galaxy's history when star formation occurred at a much higher rate than today. The densely packed stars in this region orbit the galactic center in complex paths that don't follow the orderly rotation seen in the spiral arms. From our perspective, this region appears as the brightest portion of the Milky Way, visible in the constellation Sagittarius. Though we can't see its individual stars with the naked eye due to interstellar dust, their combined light creates the glow that ancient cultures associated with milk spilled across the sky. When you look toward this celestial center on a summer night, you're gazing toward the oldest, richest stellar neighborhood in our galaxy, the first chapter in the Milky Way's long story. Some stars spend their final years in a cosmic partnership of extraordinary closeness. Symbiotic stars consist of a white dwarf, accreting material from a red giant companion, creating systems where stellar remains interact directly with their still-living partners. As the red giant's outer layers expand, some of this material falls toward the smaller, denser white dwarf, creating periodic outbursts of energy as the transferred material ignites in thermonuclear reactions. These binary relationships can last for millions of years, with each star profoundly influencing the other's evolution and appearance. The closest such system to Earth, our Aquarii, has been observed by astronomers since the 18th century. Its periodic brightenings recorded across generations of human watchers. There's something deeply moving about these stellar partnerships. How even in their final stages, stars can engage in relationships of mutual influence and shared material. Like relationships in human life, these stellar bonds transform both participants, creating something neither would become on their own. Our galaxy belongs to a neighborhood that drifts together through the Cosmos. The local group of galaxies spans approximately 10 million light-years and contains over 80 known members, bound together by mutual gravitational attraction as they move through the universe. This cosmic community includes the Milky Way and Andromeda as its largest members, surrounded by dozens of smaller galaxies that orbit these giants like satellites. Together, they move toward the Virgo supercluster in a journey that has continued for billions of years. Most of these galaxies are too faint to see with the naked eye, but on clear nights, the Andromeda galaxy appears as a fuzzy oval in the northern sky, the most distant object visible without telescopes. When you glimpse this neighboring island of stars, you're seeing light that left Andromeda 2.5 million years ago, when your earliest human ancestors were just appearing on Earth. This connection between galaxies reminds us that even the largest structures exist in community, bound to others through invisible yet profound relationships. The surfaces of ancient rocks in space bear witness to the passage of cosmic time, Many asteroid surfaces show evidence of space weathering that darkens and reddens their spectra over time, creating a patina that records their exposure to the solar wind, micrometeorite impacts, and cosmic radiation. This process gradually alters the uppermost layers of surface minerals, changing their appearance and chemical properties over millions of years. When spacecraft like OSIRIS-REx visit these bodies and collect samples, they're gathering material that carries the effects of this slow cosmic aging. The meteorites that occasionally fall to Earth often show fresher surfaces, where recent collisions in space exposed material protected from this weathering process. Your own skin similarly records your journey through time and environment, telling stories of sun exposure, healing, and growth. In both cosmic and human contexts, surfaces become records of experience, silent testimonies to journeys through time and space that leave their marks in subtle but readable ways. The rainbow of stellar colors tells stories of temperature, age, and destiny. The stellar classification system organizes stars by surface temperature and spectral characteristics, creating a sequence from hot blue stars to cool red dwarfs. This classification, originally based on the strength of hydrogen absorption lines in stellar spectra, reveals fundamental properties including mass, brightness, and expected lifespan. Our yellow-white sun sits in the middle of this sequence as a G-type star, cooler than the brilliant blue Rigel, but warmer than the ruddy Betelgeuse. When you observe the different colors of stars in the night sky, you're seeing direct evidence of their surface temperatures, from the 30,000 Kelvin of blue giants to the 3,000 Kelvin of red dwarfs. This spectrum of stellar types reminds us that diversity follows natural patterns, that differences in appearance often reflect deeper variations in nature and history. Like people, stars come in many types, each with its own beauty, characteristics, and story to tell. When stars release their outer layers, they create ghostly structures of extraordinary beauty. Some planetary nebulae exhibit complex structures created by binary star interactions during formation, producing shapes far more elaborate than simple spherical shells. The Cat's Eye Nebula contains concentric rings and knots thought to result from periodic mass ejections influenced by a companion star. The Butterfly Nebula displays symmetrical wings created by the gravitational pull of a binary partner on the expelled material. These intricate formations, spanning trillions of kilometers, yet visible from Earth through telescopes, represent a star's final creative act before its core cools into a white dwarf. They persist for only about 50,000 years before dissipating into the interstellar medium. Brief moments in cosmic time, but longer than recorded human history. In these nebulae, we see how relationships shape endings as well as beginnings, how the presence of another can transform even a star's farewell into something more complex and beautiful than it could create alone. Our galaxy holds us in its gravitational embrace with surprising gentleness. The escape velocity from the Milky Way's gravitational well at our location is approximately 550 kilometers per second, the speed needed to break free from our galaxy's pull and drift into intergalactic space. This value, about 0.18% the speed of light, represents the minimum launch velocity required for a spacecraft to leave the Milky Way entirely, never to return. For comparison, the Voyager spacecraft, the fastest human-made objects to leave our solar system, travel at just 17 kilometers per second. Despite the galaxy's enormous mass, its gravity spreads across such vast distances that its hold on individual stars remains relatively weak. When you feel the pull of Earth's gravity, keeping you grounded, you're experiencing a force 10 million times stronger than the Milky Way's pull on our solar system. Yet this gentle attraction has kept our star family together for billions of years, guiding our sun on its orbit while allowing it the freedom to maintain its own planetary system. The atmospheres of distant worlds slowly escape to space like memories fading with time. Many extrasolar planets show evidence of atmospheric escape, particularly those orbiting close to their stars, where intense radiation gradually strips away their gaseous envelopes. This process occurs through thermal escape, where the highest energy molecules exceed escape velocity, and through non-thermal processes, where stellar radiation directly removes atmospheric particles. Even Earth experiences a small amount of atmospheric escape, losing about 90 tons of hydrogen and helium daily. An insignificant fraction of our total atmosphere, but measurable over geological time. The hydrogen and oxygen atoms that leave our planet may travel for millions of years through interplanetary space before encountering another world. When you breathe, you're interacting with an atmosphere that has been carefully preserved by Earth's magnetic field and gravitational pull, protected from the same processes that have stripped away the atmospheres of less fortunate worlds. Each breath connects you to this ongoing story of planetary protection and gradual change. The colorful bands that wrap gas giants reveal a symphony of perpetual motion. The differential rotation of gas giants creates banded structure in their visible atmospheres as different latitudes rotate at different speeds around these massive worlds. Jupiter's equatorial regions complete one rotation about 5 minutes faster than its polar regions, creating shear zones where adjacent atmospheric layers slide past one another. These differences generate the planet's distinctive colored bands and long-lived storm systems, including the Great Red Spot that has persisted for centuries. Similar patterns appear on Saturn, Uranus, and Neptune, each with its own characteristic appearance, reflecting its unique composition and energy balance. When you watch weather patterns move across Earth's surface from space, you're seeing our planet's own version of this differential flow, the complex interaction of rotation, heat, and fluid dynamics that creates our climate and weather. These banded giants remind us that motion itself creates structure, that flow patterns can persist for centuries if conditions remain stable. Some stellar remnants periodically relive moments of their former glory. Some white dwarf stars in binary systems accumulate material that triggers periodic nova explosions, briefly increasing their brightness by thousands of times before fading back to quiescence. Unlike supernovae that destroy their progenitor stars, these recurrent novae occur when hydrogen-rich material from a companion star builds up on the white dwarf's surface until it reaches the temperature and pressure needed for fusion. RS Ophiuchi, one of the best-studied recurrent novae, erupts approximately every 20 years, each outburst releasing energy equivalent to 100,000 times the annual energy output of our Sun. Between these brilliant episodes, it gathers more material for the next cycle. There's something profound about these stellar phoenixes, how they gather, release, and gather again in a rhythm that can continue for millions of years. They remind us that endings often contain seeds of renewal, that cycles of quietude and expression can continue long after what appears to be a final chapter. Our understanding of cosmic distance unfolds through a series of interconnected methods. The cosmic distance ladder uses multiple measurement techniques to determine distances across the observable universe, each rung building upon the previous to reach ever further into space. Beginning with radar measurements within our solar system, astronomers extend their reach through parallax, Cepheid variables, supernovae, and redshift to map distances spanning billions of light years. Each method overlaps with others, creating a continuous chain of measurements that allows us to comprehend the true scale of the cosmos. The development of this ladder represents one of humanity's greatest intellectual achievements. Our collective effort to understand our place in the universe, despite being bound to a tiny world in a vast cosmos. When you look at distant galaxies through a telescope or in photographs, your comprehension of their true distance and scale connects you to generations of astronomers who carefully constructed this ladder of understanding, extending human awareness far beyond the limits of our physical reach. As the stars grow fainter and the cosmos quiets, our journey through these peaceful space facts comes to a gentle close. From the Terminator line separating day and night on distant worlds, to the ancient stellar streams stretched across our galaxy, we've wandered through over 100 cosmic whispers. We've explored planetary atmospheres, the delicate dance of binary stars, and the patient rotation of our galaxy around its center, 26,000 light-years from our small blue home. You are connected to this vast cosmic ballet in ways both profound and intimate. The same forces that shape planetary orbits flow through your dreams tonight. The elements in your body were forged in stellar furnaces billions of years ago, linking you forever to the quiet majesty we've explored together. As your thoughts drift into the darkness of sleep, remember that you belong among these stars. Rest now, knowing that while you sleep, pulsars will continue their precise rotations. Planetary nebulae will expand their colorful veils, and light from distant galaxies will journey through the darkness. The universe carries on its patient work as you find your own peace within it. If sleep hasn't quite found you yet, another episode awaits to guide you deeper into tranquility. Until next time, may your dreams be as vast and beautiful as the cosmos itself. Good night.